Hello ladies and gentlemen, welcome again, and today we'll be looking at the factors determining resistance of a conductor. So before proceeding with the factors that affect the resistance, let us see the definitions of some terminologies, including electric current. It is abbreviated by capital letter I. Electric current is the rate at which electric charge passes through a given point. The SI unit of electric current is ampere, and its abbreviation is capital letter A. Also, the second terminology is electric circuit. By definition, electric circuit is the closed path around which electric charge moves. Example, considering this as the electric circuit, all over here we have a closed switch, and this is our cell with a positive terminal and negative. Then this is a source of light over here. So this loop which it is closed, it is known as electric circuit, and the charge will be moving across all these components. So before getting so far, let us see how can we calculate electric current. Electric current, which is abbreviated by capital letter I, equals to quantity of charge divided by time. That's the rate at which charge moves across electric circuit. So let us look on the relationship between voltage and electric current. The relationship has been derived by Ohm's, and he formulated his law known as Ohm's law. According to Ohm's law, the ratio of voltage across a conductor to that of current is constant throughout the circuit. This is possible when other factors are kept constant. Example, temperature, pressure. Here, our constant has been determined and evaluated as the resistance. Therefore, plugging this value, whereby K equals to R, we get our equation will be as V over I equals to R. Also, in a simple way, it's volts equals to current times R. So the relationship which is found between voltage and electric current is directly proportional. Therefore, electric current is directly proportional to voltage, and this has been stated earlier by Ohm's. Therefore, on looking for the definition of resistance, which has been abbreviated by letter capital letter R, resistance, this is just the opposition a charge faces when crossing through the conductor in a circuit. So now let's get ready looking for the factors that determine the resistance of a conductor. We have 4 factors which determines the resistance of a conductor. And then the first factor is temperature. The relationship between the temperature and the resistance of a conductor in a circuit is that the increase of temperature results to the increase of resistance. This is because the increase of temperature always increases the movement of particles and electrons in the conductor. Hence, this alters the flow of current across the conductor. Therefore, it can simply be known as temperature is directly proportional to resistance. Also, factor number 2 determining resistance of a conductor is length. Length of a conductor is also directly proportional to the resistance of the conductor. This means when the length of the conductor is increased, also its resistance upon electric current also increases. Therefore, let us abbreviate the length as by capital letter L. Then, resistance will be directly proportional to length. And for this reason, we are being advised to use short wire with a short length while doing current electricity experiments. Therefore, resistance will be directly proportional to length. Let us call this as the first equation. Also, factor number 3 that determines the resistance of a conductor is cross-sectional area. The relationship that exists between cross-sectional area and resistance of a conductor is that resistance of a conductor is inversely proportional. Resistance of a conductor is inversely proportional to area. Let us name this as the second equation. So using these two equations, equation number 1 and equation number 2, we'll be able to derive the formula that will be useful in current electricity. Over here, we'll combine the first equation and the second equation. When we take equation 1, we combine with equation 2. Since R is common for both equations, then R will be, which is the resistance, will be directly proportional to length as stated in equation number 1, and inversely proportional to area as it has been stated in equation number 2. By removing this proportionality sign, it will be replaced with the proportional constant. Then it will be as KL, meaning proportional constant, over A, cross-sectional area. Of this equation, which is equation number 3, proportional constant has been determined and found to be as the resistivity of the conductor. Therefore, the proportional constant over here will be replaced by resistivity of the conductor. So our equation will be is resistance of a conductor equals to resistivity, length of a conductor, then divided by cross-sectional area of the conductor. Over here we get another factor that determines the resistance of a conductor, which is resistivity. So factor number 4 will be resistivity. The relationship between resistance and the resistivity, that the change of resistivity of materials will also alter the resistance of a conductor. Example, steel have high resistance than copper. This is due to their difference in resistivity.